Hello, welcome to my coronavirus classroom. I'm Janessa Jacobs, and this is the digestive and urinary exam review. I'm supposed to be speaking on my microphone right now. I'm sure that it heard it. It adds to the ridiculousness, which is all part of what we're going for in our exam reviews in the living room. Okay, so to begin, the digestive system, A, extracts nutrients. B, excretes wastes. C, secretes enzymes. D, all of the above. E, A and B only. All right, the digestive system does all of the above. It extracts nutrients. I looked up the definition of this word extracts to make sure that I was using it appropriately. And extracts means that you're doing hard work to pull something out. And the digestive system is definitely doing hard work to pull your nutrients out of the stuff that you stuff into your face. Okay, the urinary system. A, extracts nutrients. B, excretes wastes. C, secretes enzymes. D, all of the above. E, A and B only. So this time the answer is E, A and B only. And if you look back here, the answer actually doesn't have A and B only here. Because I decided to ask this question for the urinary system, I had to change it. So I went ahead and added A and B only to the digestive system for you. The digestive system is excreting waste. We're pulling all of our waste out of food, and then solid waste is being excreted. And the large intestine helps with all of that, and the rectum and colon void it from your body. The entire lumen of your GI tract is secreting mucus, but your stomach really starts secreting some nice digestive enzymes. I mean, saliva has some enzymes in it, but your brush border enzymes, so definitely important throughout the digestive system to be secreting enzymes. So now if we come to this urinary system question, why is the answer no longer all of the above? And why is the answer, this is actually the reason that I looked up the definition of the word extract, was to see if I could use this same question for this different system. And I figure I can. Because if extracting is doing hard work to get something out, then the urinary system is extracting nutrients. It's doing hard work to get nutrients back out of the fluid that got filtered out in glomerular filtration. So as you move into the nephron and start pulling things out of the stuff that's becoming urine, that's hard work. And we're bringing back all of our nutrients, glucose, amino acids, everything that we need. And this is how we're going to excrete our liquid wastes. Now, I was thinking I could hear some potential arguments for, well, it secretes. It's not secreting enzymes. It's not secreting any kind of digestive enzymes or anything into the fluid. Tubular secretion is happening, sure, where we're pulling things that are unwanted from the blood and secreting it into the fluid that's becoming urine, but that's not enzymes. So our stomach secretes digestive enzymes. Our brush border enzymes are secreted by the small intestine. So that's why it works for the digestive system, but not the urinary system. Okay, and that's the last time, for now anyway, I think you get to see one of my questions. Okay, the blank is an important accessory digestive organ. A, stomach. B, small intestine. C, liver. D, all of the above. The answer is C. Liver is an accessory organ. I mean, what I probably should have done is none of the above. That might have been more confusing, because you could say it's probably pretty obvious that the stomach and small intestine are accessory digestive organs because they're part of the GI tract. So if I had said none of the above, then maybe you would have thought, oh, the liver's not an accessory. It sure is. That's the answer. Okay. Blood filtration requires A, the kidneys, B, the ureter, C, the bladder, D, all of the above. So this is a urinary system question, and the kidneys are filtering the blood. All right, blood filtration requires A, the stomach, B, the small intestine, C, the liver, D, all of the above. Okay, this is a digestive system question, and the answer is C, the liver. The chemical digestion of proteins occurs A, in the mouth, B, in the stomach, C, in the pancreas, D, all of the above. The chemical digestion of proteins occurs in the stomach. So the mechanical digestion of everything begins in the mouth. The pancreas isn't digesting anything in it. It's digesting everything when we consider that it's producing pancreatic juice that gets released into the duodenum, but that's the small intestine. So in the small intestine, sure, pancreatic juice is digesting proteins, but not in the pancreas. When thinking of urine formation, the blank is probably the most important part of the nephron. A, proximal convoluted tubule, B, nephron loop, C, distal convoluted tubule, D, all of the above are required for urine formation. All right, so the answer is A, the proximal convoluted tubule. And you might say, yeah, but all of the above are required for urine formation. And that is true. But the question is not asking you what is required for urine formation. It's not saying what processes are required for urine formation. It says when thinking of urine formation, this is probably most important. Why is the proximal convoluted tubule probably most important? Because it reabsorbs something like 65% of filtrate, because it does like 80% of the entire adjustments to blood and urine that are occurring. So the proximal convoluted tubule is doing most of the work. So that's why it's the most important for urine formation. Now, what if we had to think about the blank is most important for osmotic pressure? What if that was the question? Which part's most important for osmotic pressure? Well, that's going to be the nephron loop, and specifically juxtamedullary nephron loops, right? Because on the descending limb, they're letting water out, and that's being picked up by the vasa recta. And then on the ascending limb, they're letting salts out that get stuck in the interstitial fluid. So yeah. Okay, the blank is most responsible for chemical digestion. A, mucosa, B, submucosa, C, muscularis externa, D, serosa. The answer is A, the mucosa. Yeah, that's what's in contact with the food, right? Right. Now what if instead this said the blank is most important for motility? What would that be? The muscularis externa, right? Right. Now what if it said the blank is most important for enteric nervous system activation? That'd be submucosa. The biggest branches, I think, the biggest branches of our enteric nervous system are coming in through the submucosa. So yeah, all right. All good things to think about. If a person were to have high levels of sodium in their body, but low levels of antidiuretic hormone, what would you expect to see? A, an increased amount of urine production. B, dilute urine production. C, thirst. D, all of the above. Oh, here we would expect to see all of the above. So this is actually something that I didn't mention ever this semester, but I really wanted to. Because it helps you understand how antidiuretic hormone is working. If you inhibit antidiuretic hormone and don't have any of it, then what you do is you increase the amount of urine that is being produced, and it's dilute, and you get thirsty. Why is this, and who takes advantage of it? The bartenders take advantage of it. They give you a bunch of peanuts, which are salty, or a bunch of popcorn, which is salty, so that you've got a lot of salt in your blood, and we reabsorb salt because it's really important to do that, because it's going to try and get us to reabsorb water, right? If we reabsorb salt, then water's going to follow, so we reabsorb all of that salt that's coming through. But now let's imagine what has happened here is in the nephron loop, we created this really salty interstitial fluid, and now we don't have antidiuretic hormone. So the material that's passing through here, if we pumped out water here that got picked up by vasa recta, and it was salty here, and now we pumped out all the salts here, then now what's coming through here, sure, is some water. Yeah, this is dilute urine that's coming through here. It's really salty out here. And now when we get here, normally what happens is antidiuretic hormone is going to be present, and so we'll bring the water back into the body because this salty interstitial fluid is going to create this osmotic pressure gradient. Well, alcohol inhibits antidiuretic hormone. So when you drink alcohol, you don't have antidiuretic hormone, so you don't get these aquaporins produced in your collecting duct. So instead of reabsorbing that water to this salty interstitial fluid, you just increase the amount of urine you're producing, and it's dilute because we pumped all the salts out here and left them out here. We're not reclaiming water because there's no antidiuretic hormone, and you get thirsty. Why you get thirsty? Because your hypothalamus knows that you've got a lot of salt in here, and so you're going to need to drink more. So what do? You order another beer, and they give you more peanuts, or they give you more popcorn, and they get you in a positive feedback loop of salt, causing you to get thirsty, causing you to buy more alcohol, causing you to eat more stuff, and all that. It's quite ingenious. Those bartenders. Okay. All right. Peristalsis and secretion are important functions of A, salivary glands, B, pancreas, C, stomach, D, all of the above. Ah, the stomach. Okay, now I know some of you are sitting at home right now and you're like, wait a minute, all of the above, because salivary glands and pancreas secrete stuff. That's true, they secrete stuff, but they don't do any peristalsis. This is saying peristalsis and secretion are important functions of what? The stomach. All right, that wraps up all of my questions. I thought I would like to do a just quick review of both systems. So let's do that, and then you can shoot all of your questions to me in the Teacher Helping Students Succeed discussion board. Okay. So, how can we review both systems real quickly? Superior to inferior, that's how. Okay, so if we think about the digestive system, we said that it was important to think about specializations in the wall of the alimentary canal, what the different organs were secreting, what they were digesting, what motility was going on, all that. So let's just sum it all up. So digestion begins in the mouth. So here's our oral cavity. It's going to lead into our pharynx. It's going to lead into the esophagus. It's going to lead into the stomach. It's going to lead into the small intestine. Ooh, it's going to lead into the large intestine. I'm going to switch colors for the large intestine. And our large intestine is going to continue across and down. Okay. So, mouth. We ingest food, so that's an important process that's occurring there. What are the organs? The teeth, the tongue, the salivary glands. So what are we secreting? Saliva. As far as important components, salivary amylase is going to begin carbohydrate digestion. Lingual lipase is going to be introduced into the food there. The motility that's occurring is that we have the voluntary phase of swallowing, where you're kind of pushing the food back and forth between your tongue and your teeth and mixing it with saliva and forming this nice swallowable bolus. You'll start pushing that along your hard palate. When you get back to the soft palate, you're going to stimulate tactile receptors that will push your uvula up to block your nasopharynx. Your epiglottis is going to flop down and block your larynx so that food can move through your pharynx to your esophagus. What else is going on in the oral cavity? We're secreting, there's a lot of mucus there. If we think about the wall, our epithelium is stratified squamous epithelium, the non-keratinized version, because it's got to be wet. We see that through the oropharynx and laryngopharynx and through the esophagus. What else? So that was, we got to think about our wall secretions. We just have a lot of saliva and mucus. Think about digestion. We're doing our mechanical digestion. Mechanical digestion beginning as your teeth tear and grind your food. Chemical digestion is beginning as salivary amylase begins breaking down your carbohydrates. Absorption is standard. Anything that's lipid soluble, if the cells need water and glucose, we can absorb that as well. Motility is the voluntary phase of swallowing. Then we move into the pharyngeal, esophageal phase of swallowing, which is involuntary. And as far as the wall goes here, this is still our stratified squamous epithelial tissue, the non-keratinized type. We're secreting a lot of mucus, not a whole lot of digestion occurring here, only our standard absorption, and the motility is peristalsis. This peristaltic wave is going to open up this cardiac sphincter, this ball of food, this bolus is going to enter your stomach and be mixed with gastric juice. So the wall of the stomach has gastric pits. The parietal cells are secreting hydrochloric acid. The chief cells are secreting pepsinogen that gets converted to pepsin, and that's going to begin the chemical digestion of our proteins. Hydrochloric acid breaks our proteins, denatures them into their primary structure, and then the pepsin is going to go in there and start breaking that protein down into polypeptides. As far as absorption goes, standard absorption. The motility, we've got peristalsis that's going to move the food forward, and then we get this forceful mixing and grinding here in this pylorus region, and then we're going to open up this pyloric sphincter. A little bit of chyme is what we'll call it now, is going to pass into the duodenum of the small intestine. The pyloric sphincter snaps shut, the food moves back in this like retropulsion thing. So for the pharynx and esophagus, I'm not going to write all that down, it's not horribly important, and you can go review your other videos. For the stomach, for the wall, we've got gastric pits. Other things, we've got an extra layer of muscle in the muscularis externa, and that is going to help with that forceful mixing and grinding. The digestion, what we could say here, we've got some mechanical digestion as we break the material down with that mixing and grinding, but the chemical digestion is that our proteins are being denatured and then broken into polypeptides. Chemical digestion of starches stops. Salivary amylase becomes inactivated in the low pH of the stomach. Gastric lipase is added, but lipid digestion in the stomach is negligible. As far as absorption goes, it's standard. Motility, we've got peristalsis, but we also have mixing and grinding, and we get retropulsion. For our small intestine, when the material moves into the small intestine, it's called chyme, and bile is going to be added, and pancreatic juice is going to be added. So the small intestine itself is really only secreting brush border enzymes, but it's receiving the juices, the digestive secretions from our accessory glands. And our small intestine is really important in finishing up chemical digestion and doing all of our major significant nutrient absorption. So for the small intestine, as far as its wall goes, we have columnar cells with microvilli. That's one way. Each cell increases its own surface area. So that's going to be one thing that it does to specialize. The second thing that it does is it has these things called intestinal villi. And that occurs, and that's due to the folding of the mucosa. It's due to the folding of the epithelium and lamina propria on the muscularis mucosae in the mucosal layer of the small intestine. So the innermost layer that's in contact with the food. So this is folding of the epithelium and lamina propria on the muscularis mucosae. The second way that we increase our surface area. And then the third way that we do it is that we make the submucosa and the mucosa longer than the muscularis externa so that it cinches up as well and creates what are called circular folds, or the plicae circularis. And this is folding due to, I'll say the folding of the mucosa and submucosa on the muscularis externa. So that's really the most important specialization of its wall. The small intestine secretes brush border enzymes. And brush border enzymes are going to finish chemical digestion. So chemical digestion really began in the mouth and stomach, and our brush border enzymes finish it. So the middlemen are the digestive enzymes that come from our accessory glands. So the pancreas is going to be sitting here producing pancreatic juice that gets added to the duodenum. And then the liver is sitting back here filtering blood and producing bile that the gallbladder is concentrating. So the gallbladder stores and concentrates bile, and that is going to get added to the duodenum as well. So that the bile is going to act as the middleman for fat digestion and really help to emulsify those fats. The bile salts are going to wrap around and create these things called micelles, and then pancreatic juice can get down in there really and break it down. And then the small intestine is going to absorb that as chylomicrons, and the fats go into lacteals that are taken, then draining into the cisterna chyli, and that fatty lymph is going to drain from the thoracic duct and back into your left subclavian vein. The other nutrients are going to be digested by our pancreatic juice. Our carbohydrates are going to be broken down. And then our brush border enzymes are going to break those down into monosaccharides. They're also going to help with the breakdown of our polypeptides. The brush border enzymes break those down into amino acids, and that's what we're absorbing. So if we think about what's being secreted by the small intestine, we could say our brush border enzymes are being secreted by the small intestine, but it's also receiving pancreatic juice and bile. So if we think about the digestion that's occurring here, we're taking these polypeptides to like anywhere from 2 to 8. So 8 is like oligo, so di to oligopeptides. That digestion is occurring because of pancreatic juice. And then from those kind of larger of the small peptides, we're going to get down to our amino acids, and that's happening because of the brush border enzymes. Okay, for carbohydrates, we've got polysaccharides that are going to be broken down again into disaccharides up to like oligosaccharides, and that breakdown is happening by our pancreatic juice. And then when we go from these disaccharides down to our individual monosaccharides, that is handled by the brush border enzymes. Lipids we just talked about. Lipids are getting emulsified. So fat, we come in as a large fat droplet. It gets covered in these bile salts to become this thing called a micelle. Then pancreatic juice gets in there and breaks it down into free fatty acids and glycerol. Those get absorbed as chylomicrons and empty into lacteals. Our amino acids and our monosaccharides are being absorbed into normal capillaries that are going off to the hepatic portal system to be filtered. So as far as other things in the small intestine go, absorption. What are we absorbing? All of our major nutrients. We're doing water, we're doing vitamins, we're doing minerals, we're doing amino acids, we're doing monosaccharides, we're doing chylomicrons of these free fatty acids and glycerol. Motility. Peristalsis is going to be the major means of propulsion, but here we also have segmentation, which are those small side-to-side contractions of the wall that help with mechanical digestion, but also some propulsion. When we get to the large intestine, the wall, really the only specialization is that we got a bunch of goblet cells so that we can secrete a bunch of mucus. So secretion, a lot more mucus in the large intestine, because what's happening here now is we're reclaiming our water and producing solid waste. So we need to lubricate that material. Digestion. The large intestine does does no digestion of its own. The bacterial flora that live in your gut will digest your indigestible and undigested materials and release methane. They also release the vitamins B and K, which you will then absorb. So if we look at absorption in the large intestine, it's water, vitamins B and K. For motility, peristalsis, as always. But then we also have these haustral contractions that move material from one haustrum to the next. And then mass movements that start about midway through your transverse colon. They're forceful contractions that push things from the sigmoid colon through to your rectum, and they should lead to a bowel movement. So that's the digestive system. Let's have a quick review of the urinary system. Okay, so for a quick review of the urinary system, let's zoom into the nephron, where we have two parts, right? A renal corpuscle and a renal tubule. So I'm drawing out the renal tubule right now. Proximal convoluted tubule leads into the nephron loop, leads into the distal convoluted tubule. That's the nephron. Here's the renal corpuscle. This is my glomerular capsule. Here's my glomerulus. Okay, so in the glomerulus, what happens? Filtration, right? So the hydrostatic pressure here is going to be greater in the glomerular capsule because our afferent arteriole is wider than our efferent arteriole. So we put a lot of pressure on here and we push everything out of the blood except our cells and large proteins, so that what we collect in here is this stuff called filtrate that's in chemical equilibrium with blood plasma. So there's not really a whole lot exciting happening here. The process occurring in the renal corpuscle, which has two parts, right? The glomerulus and the glomerular capsule. The only thing happening here is glomerular filtration. Horribly important, but not horribly interesting. So remember, glomerular filtration rate is the most important thing for determining the rate of urine formation. So the kidneys have myogenic and tubuloglomerular feedback mechanisms that they can do for self or auto regulation of glomerular filtration rate. And then the body, in response to systemic blood pressure changes, can adjust glomerular filtration rate to maintain systemic blood pressure. So I'm going to let you rewatch the video if you want to see that again. When we get to the proximal convoluted tubule, this is where we're going to be making most of our adjustments to urine. So we're going to be reabsorbing or bringing back everything that we want. So as far as our tubular reabsorption goes, tubular reabsorption in the proximal convoluted tubule, we're going to bring back some water. We're going to bring back our vitamins and minerals according to need. We're going to bring back amino acids. We're going to bring back glucose. So we're pulling it out of the fluid and bringing it back to the body. What are we going to concentrate in the fluid? So things that I can secrete here. Hydrogen ion if my blood's acidic. Ammonia. I can do urea, uric acid. So this is where we're really going to be secreting most of our wastes. Drugs, excess hormones, excess ions. We're going to do a lot of tubular secretion of those things there in the proximal convoluted tubule. Okay, when I move to the descending nephron loop, I'm going to have water reabsorption, and this water is going to be reabsorbed into the vasa recta. So it doesn't stay here and change what's going to happen with the osmotic pressure gradient that we're trying to create here. So in the descending nephron limb, we reabsorb water, so we are reabsorbing it to the blood. And it's being picked up in the vasa recta. Then we cross this hairpin turn. When we get up to the thick limb, or the thick-walled ascending limb, we're going to start reabsorbing salts. So we will reabsorb salts, but we're only bringing these back to the interstitial fluid. So what this is going to do is it's going to get really salty out here. This is what creates the osmotic pressure gradient that will allow for maximal water reabsorption in the collecting duct. Okay, when we get to the distal convoluted tubule, secretion and reabsorption are under hormonal control. So if we were thinking here, tubular reabsorption in the distal convoluted tubule. If parathyroid hormone is present, we will reabsorb calcium. If aldosterone is present, we will reabsorb sodium. If antidiuretic hormone is present, we will reabsorb water. As far as tubular secretion in the distal convoluted tubule goes, potassium is going to go the opposite way of sodium. So with aldosterone present, we would have tubular secretion of potassium. If calcitonin was present, we would have tubular secretion of calcium. This is also an area that can act as a buffer. So if we have to excrete excess hydrogen ions or something like that to help with blood pH, then we can do that here. From here then, we will move into little collecting ductules that drain into collecting ducts. In the collecting duct, we're really only going to be reclaiming water under the influence of antidiuretic hormone. There we can act as a buffer system as well if we need to adjust hydrogen ion concentrations, but really in the collecting duct, which is not part of the nephron, all we're doing is reabsorbing water and concentrating our urine. So that's the most complicated part of that. So you're in luck. The test is almost here and I'm almost done making that stupid joke. See you soon.